Good morning, my dear members. Hope you're all doing well. In the previous discussion, we discussed about example 2 of transient circuit analysis. In that example, we shared an assignment that didn't go about with you. So I request you that we go through it together here and you correct yourselves. I'll be glad if you leave the questions in the comment section where you have not understood well. In transient circuit analysis, I told you what you have to do first is to determine the storage devices in the circuit. Storage devices can include capacitors, inductors, and other storage devices. Here we are having inductors, capacitors. In most cases, transient circuit analysis, we deal with capacitors where we have rate of change of current, and inductors where we have rate of change of magnetic flux. So in this case, we are going to analyze this circuit and we see how we can determine the current flowing through the circuit at any time t. As I told you before, for a DC source, the capacitor acts as an open circuit, it blocks DC, and an inductor acts as a short circuit. When you look at that diagram, we redraw it at time t equals 0. When we revisit our first diagram, you can see clearly that the capacitor will act as an open circuit and inductor is shorted. So the very large current goes through the path of an inductor. Because there is no current will go through the path of the capacitor since it is open circuit, so we deal with a loop equation with only the 36 volt DC source. Let us now consider the outer loop. Current IL can be determined using Ohm's law and it's obtained by dividing the DC voltage supply by the resistance in that circuit. Now, considering the outer loop, when we take the outer loop of the circuit, we are seeing we are having open circuit voltage across the capacitor position. So when we revisit how the loop is taken, it is in clockwise direction. So we are having negative 36 plus 4IL plus, now the current that will go through the open circuit voltage, we don't know it, but we know the voltage across the open circuit, which is now plus VOC plus the 12 volts will give us 0. Simplifying that equation, we get the open circuit voltage VOC as negative 12 volts. At time t is greater than 0, we have that switch opening. When the switch opens, the loop of the 36 voltage supply is now outside our circuit. So the only circuit diagram we have is that closed loop 1. So taking loop 1, we are having the voltage equation KVL. So using KVL, that's Kirchhoff's voltage law, we get voltage across the inductor plus the voltage across the 4 ohm resistor plus the voltage across the 2 ohm resistor plus the voltage across the capacitor plus the 12 voltage source gives us the total voltage, which all sums to 0. So the total algebraic sum equals 0. So that is the loop equation of that circuit diagram. Simplifying the equation by substituting the inductance of the inductor, which is 1 Henry, plus 4 plus 2 ohms gives us 6 times the current I at any time t, plus the voltage, which is 1 over C integral from 0 to t of current, gives us a 0. Now, transforming the above equation into Laplace transform, which is the S domain, gives us the equation below. So this is the equation we are following, this equation. Simplifying the above equation gives us equation 2. So we can use partial fractions to determine the equivalent fraction ratios of the above fraction. So if you need to know how to determine easily the brackets for that second order polynomial, we can do it together here on a calculator. You go to the mode, then you go to equation 1, then you go to degree 2, then the coefficient of the equation. What am I talking about? The coefficient here is 1, coefficient here is 6, coefficient here is 1. So the coefficient of A is 1, that is at S. The coefficient at S is 6, and the coefficient of the constant C is 1. When you press equals, it brings negative 0.172 and negative 5.828. So that is how I determine those two brackets. Hope we are together. Now, expressing the expression into partial fractions can be done in an easy way. When you multiply this expression in the denominator of coefficient A, will give us by this, so that here it will cancel with what will be there. So we remain with only A as the unknown. Now if we substitute s as negative 0.172, it will give us a 0 here because it will phase out. Similarly, when we multiply it this side, this expression in the denominator will phase out and remain with only this one. That's why I have this equation. So expression a constant will be equal to 9s over s plus 5.828 at a value of s equals negative 0.172. Similarly, we determine b in the same way, and we get a and b as these constants. Replacing back the constants, we determine the total fraction in the s domain of the current I of s. Transforming the current I of s into a time domain function, it gives us the expression required. Thank you for watching. Subscribe, like, and share this video with your friends. It is valid for all universities. Thank you for watching.